5.7, apply the fundamental theorem of algebra. We're going to classify the zeros of polynomial functions. That means we're going to be able to look at a polynomial and know how many zeros there are, and then we're also going to figure out what those zeros happen to be. This page tells you that if the degree is n, you're going to have n zeros. They could be rational numbers, they could be irrational numbers, they could be imaginary numbers, but there's going to be n of them. Some of them repeat. Repeating means maybe you factor, get something like this. Says we have 3 factors, so the zeros are 2 and -3. You might be thinking, now, Mr. Clinton, you just lied to me. You said there'd be 3 zeros. There are. We count this one twice, so we say multiplicity 2, meaning it shows up twice. And I don't see the word multiplicity on this page, but that's what it means when we have the same zero show up twice in a factorization. We should be able to find all 3 in a cubic, all 4 in a quartic, and so on. That being said, how many solutions does this first equation have? Well, it's the 3rd degree, so it has to have 3 solutions. Part B, how many zeros does this next function have? It's a 4th degree, so it must have 4 solutions. Wouldn't it be nice if the whole lesson stayed this easy? It's not going to. So you can go ahead and pause the video, try these on your own, or you can do that later. We've got a 5th degree, which means we've got to find how many zeros? 5. And they're not going to be easy to find. We don't know how to factor a 5th degree by any means. What we do know how to do is use the rational zero theorem, meaning you've got to make that PQ list and list out all the factors for P, all the factors for Q. I'm not going to do that part for you because you need to know how to do that on your own. What I will tell you is pause the video and try to find them. I'll tell you right now there's 3 numbers that work. It says there's 5 zeros, but only 3 of them are rational, which means only 3 of them are going to be from the P or Q. We don't know what ones they are. See if you can find them on your own, and I'll tell you what they are momentarily. You got to be able to come up with them on your own and do that synthetic substitution, though. Go ahead and pause. Turns out, after you go through the nightmare that is the rational zero theorem, we end up with factorizations like this. And that last factorization doesn't factor nicely, but you can use the quadratic formula for it. And if you do so, you get 2 plus or minus I squared of 3. Again, you need to be able to do that on your own. Make sure you know how to. The -1 worked twice. So we say x equals -1 is a 0. And the multiplicity is 2 because it shows up twice. And x equals 2. If you count them, we got 5 zeros. -1, -1, 2, 2 plus I squared of 3, 2 minus I squared of 3. You should always be able to find your 5 zeros. Again, the only way to get this thing started is by using the rational zero theorem and finding something that works. Graphing calculator saves you a lot of time there. Even a scientific calculator could. At this point, you can pause the video and try some of these on your own. Otherwise, you can do it later. Complex conjugates theorem. This tells us if you know a zero, for instance, if I know 3 plus 5i is a 0, turns out that 3 minus 5i is also going to be a 0. Zeros come in conjugate pairs. That's true for imaginary numbers and irrational numbers. So for instance, if 4 minus 3 squared is 7 is a 0, 4 plus 3 squared is 7 is a 0. We haven't really worked with conjugates since we were simplifying fractions with square roots in the bottom, but they're coming back for this lesson. We'll see how that applies shortly. Next up, it says we're going to write our own polynomial of least degree, meaning if we can make a 3rd degree, let's make a 3rd degree. And we're told the leading coefficient needs to be 1, and it gives us 2 zeros. If you remember from the last slide, since 2 plus square root of 5 is a 0, 2 minus square root of 5 has to be a 0 also. Now we can write out our factors. we got x minus 3, x minus this whole thing, so that means this minus sign distributes, and x minus this whole thing. Again, the minus sign has to distribute. Looks kind of messy. That's going to be our least possible degree. And guess what I'm going to expect you to do from this point? Multiply it out. Good thing's going to happen. All the square root stuff's going to cancel out every time. So when you multiply these two together, you shouldn't have any square root in that piece. And I'm going to put up what that solution is. I strongly recommend you try it on your own. Make sure you get the same thing. After that, all that's left is multiplying through, which you should also practice on your own. Make sure you get the same thing as me. So what we really did here today is what we've been doing in the previous lessons, but backwards. We used to start off with the final answer here, and I tell you to find all the zeros. Now I'm telling you the zeros, and you're finding the polynomial. At this point, you can pause the video and try these on your own, or you can do that later. Descartes' rule of signs tells us the number of positive and negative real zeros there might be. Real zeros, not rational. So if I tell you that there is a real zero for sure, that doesn't mean you should only use positive numbers when you're doing your PQ test. You've got to keep in mind that it could just be a number that's not a fraction, like square root of 7 might be a 0. And to figure out how many positive real zeros there are, we count how many times the sign changes in the original problem, and that's the most we could have. Then we subtract 2. For instance, if we count the number of sign changes and there's 7, we subtract 2, we say there could also be 5, or 3, or 1. We lower by 2. If it turns out we have a lot of positive ones, we want to try plugging in positive numbers. If we have a lot of negative, we want to try plugging in negatives. Descartes' rule of signs is really just there to save us some time. So let's take a look at it. And before I do that, let's talk about the negative zeros. They're a little harder. We have to go in and plug negative x into the original problem, and then count the sign changes again. We'll see what that looks like in the next example. So we want to find out how many times the sign changes. Starts off with a positive, then a negative, a positive, a negative, a negative, a negative, a negative. So how many times does our sign change? Changes once, changes twice, changes 3 times, and it doesn't change anymore. It stays minus after that. So we saw 3 positive real zeros. And we can lower that by 2, because there might also be 1 real zero. We try lowering that by 2 again. You can't have a negative number of zeros, so we can't do anything there. Next, we figure out what's f of negative x. That means we put negative x into the entire function, which really means just change a sign on the ones with an odd power. Even powers, like 6, don't change. Odd powers, like 5, do. Plus 3x to the 4th, plus 10x to the 3rd, minus 6x squared, plus 8x minus 8. So I'm really just changing the sign on everything that has an odd power. Then I look to see what my positive and negative signs look like. Looks like it changes 1 time, 2 times, 3 times. So I could have up to 3 negative zeros, which would leave complex zeros, meaning imaginary, to 0. We couldn't have any in this case. Why? Because the original function was to the 6th power. If we had 3 positive and 3 negatives, we'd have 0 complex. We could have 1 positive and 3 negative, which would leave 2 complex. We could have 3 positive, 1 negative, 2 complex. Could have had 1 positive, 1 negative, and 4 complex. So here's the different scenarios that might happen. Any one of these 4 might happen. We don't know which one. It'd take a lot more investigating to figure it out. That determines the number of possible positive real zeros, negative real zeros, and imaginary zeros. Try this on your own using Descartes' rule of signs, or you can do that later. Next up, we've got to find the zeros of this guy, except that it says approximate the zeros. You're going to want to go check in with the graphing calculator supplement. You're going to graph this in the graphing calculator and use the zero function to find them. You'll notice this is way faster than any other method of finding zeros that we've learned. We don't have to do Descartes' rule of signs. We don't have to do the PQ test. We don't have to factor. We just have to choose an appropriate window on our calculator and find the zeros. Again, you can find information on that on the supplemental. Turns out there's only 2 real zeros. The rest of them, that means, are complex zeros, imaginary numbers. Or these might be multiplicities. You have to see where they land on the graph. Next up, go ahead and pause the video and try to figure out what's going on here. We're told that the boat's going 15 miles per hour, so we're trying to find the speed of the engine shaft, that's x. And notice these decimals do not make the problem look any easier. In fact, we'll never learn how to factor something with decimals like this. This is another graphing calculator problem where you'll solve for x by looking at the graph. And it turns out you get x equals 19.86 once you look at the graph. Information will be there on the supplemental portion for this section. And just to give our final answer, that's in hundreds of RPMs, so we've got to multiply that by 100. 1,986 RPMs. That's how fast our engine shaft is moving. That's it. At this point, you could pause the video and try these on your own, or you can do that later. That's it for